Hello friends, welcome to this video. In this video, we are going to implement another biomedical image segmentation architecture called ColonSegNet. ColonSegNet is an encoder-decoder architecture developed for the purpose of polyp segmentation. Here the encoder learns to extract all the necessary information from the input, which is then passed to the decoder. The decoder uses this information to generate a segmentation mask. The ColonSegNet uses Residual Block with Squeeze and Excitation as the main component. The network is designed to have a very few parameters as compared to other baseline architectures such as UNET, PSPNet and DeepLabV3. The use of very few parameters make the ColonSegNet a lightweight network that leads to real-time performance. So now let's have a look at the block diagram. So here you can see the network is built using different blocks, and beside each block you can see the height and width of the output feature map. This height and width show you how the initial input image is transformed when it passes through different layer, and at the end of the network we get our segmentation mask exactly of same height and width as our input. So here the left part of this image is the encoder and the right part is the decoder, and in between we have multiple skip connection connecting to the decoder. So these skip connection transfer information from encoder part to the decoder part of the network. So this information is really important as it contain a lower level features such as edges and other things. And some information in the network is also lost due to the depth of the network. So this skip connection also help in direct flow of information. So first of all, let's try to implement these different convolutional block in the ColonSegNet, like this residual block, strided convolution, as we also use squeeze and excitation. So let's first of all let's try to implement these blocks, and then we'll try to work on the entire network. So here we are going to import all the required layers. Let me zoom a bit. So we have executed this cell. Now we would work on the squeeze and excitation. So here's a block diagram of the squeeze and excitation block. So you can see it has three steps: squeeze, excitation and scaling. So in the first step, we take the input feature map and we apply a GAP layer, that is global average pooling layer. This squeeze the feature map and we get a global level features. After the squeeze step, we have excitation where we apply a fully connected network, and at the end we apply a sigmoid activation function. So the one of the main property of sigmoid function is that if you give it any value, it would convert it in a range of 0 and 1. So 0 and 1 basically act as a attention. So the output of the second FC layer, that is fully connected layer, pass through the sigmoid. So it would generate a segmentation map of which have a value of 0 and 1, and this 0 and 1 is basically multiplied in the scaling step with the original input. So this multiplication here would act as a soft channel wise attention mechanism, and this process basically remove unwanted feature and highlight the important features, and we get the output. So let's try to implement the SE layer, that is squeeze and excitation layer. So it's going to take the input feature map as X, then it's going to have number of filters, and then we're going to have another variable called reduction with a value of 16. So first of all, we are going to save our original input in a XINIT. After that, we are going to apply the global average pooling layer. We're going to give it the input X. After that, we're going to apply some dense layer. So we're going to say dense, and within the dense layer we are going to reduce the number of filter. So here you can see in the dense layer we divide number of filter with this 16. This is just to reduce the number of filter so that it is light in weight, it is not that heavy. And here we say use bytes equals to false, and the activation function is relu. So our next dense layer would have an activation function, that is sigmoid, and here again we are going to change the number of filters to the original input number of filter, and instead of relu we're going to say sigmoid. So this way we generate an attention map, a channel wise attention map. Now we're going to multiply it with the original input. So we're going to say x equals to, or you can say return x init into x. So this is done. Now we're going to execute it. Our next block is the residual block. So you can see this is the residual block. It begins with a convolutional layer, batch normalization and a ReLU. Again it is followed by a convolutional layer, then a batch normalization. Now after that we take the input, we passes through a pointwise convolution, that is 1 by 1 con 2D layer, followed by a batch normalization. Then here we apply the squeeze and excitation. So it is a channel wise attention mechanism, and then we join or sum both the feature, or add or perform an element wise addition over both the feature. Then it is followed by a ReLU layer. So the introduction of this shortcut connection helps to transfer the feature from input to the output. So it helps to learn an identity mapping. So now let's try to implement the residual block. So it's going to take the input feature map as x and the number of filters. So number of filters are basically number of output feature channels. So we're going to say x init and we're going to save the original input. Then we have our convolutional layer. First number of filters, then we're going to have the kernel size, then padding equals to same. So padding equals to same means that if your height of the feature map, or if the height and width of the feature map are, let's say, 128 by 128, so when we say padding equals to same, so the output feature map from this convolution layer would also have same height and width, that is 128 by 128. This we done so that there is no confusion or change in shape. Slight change in shape can cause issue while concatenation. Then this layer is followed by the batch normalization. After that it is followed by the activation function. Here we use ReLU activation. So our initial 3 layers are done. Now we have another convolutional layer, and a batch normalization. So I'm going to copy it directly from here. So this is done. Now we need to work on our shortcut connection. So we're going to say S equals to con 2D. Number of filters would be same. The kernel size would be 1 and padding equals to same. Input would be x init. And again S equals to batch normalization. Now here we're going to apply the squeeze and excitation layer, that is SE layer. We're going to give S as the input feature map and number of filters. So this way we have completed this shortcut connection. Now we're going to add both the features. So we're going to say X activation. So if you remember, after when we add those features, it passes through the activation function. So in the input we're going to say X plus S and we're going to return the X. So we have built a simple residual block. Now it's time for the strided convolution. So strided convolution is really simple. It contains 3 layers, and the first layer is con 2D where we apply stride value of 2. So when we apply stride value of 2, it reduces the height and width of the feature map by a factor of 2. Let's say your input size is 128 by 120, then your output size would be 64 by 64. So let's implement this simple strided con block. So input feature map would be X, then number of filters. So here we're going to say X equals to con 2D. First it would take number of filters, then a kernel size. After that we're going to apply stride and padding equals to same, and input would be X. Then it is followed by the batch normalization, and a reload activation function. Okay, the mistake here, it should be in the quotes and X. Now we are going to return the output of the activation function. So this is done. So now we have implemented all the three blocks, that is squeeze and excitation block, residual block, and strided convolution block. Now it's time for us to build the encoder block. So let's again go back to the diagram and see. So if you see the encoder block, these are the two encoder blocks. So if you see in the first encoder block, we have residual block, strided convolution, residual block, and a max pooling. In the second, we have residual block, strided convolution, and residual block. So in the second, we ignore the pooling layer, we do not include it. So let's try to implement these layers in an encoder block. So here we're going to say def encoder block. So it's going to take X as the input and number of filters. Okay, so if you remember, first is the residual block. So we're going to say x1 equals to residual, then X as the input and number of filters. After that, it is followed by the strided con block. This time input would be x1, that is output of a residual block, then number of filters. Now third layer would be a residual block, its input would be x2, that is output of strided convolution, then number of filters, and finally we're going to have a pooling layer, a 2 by 2 pooling layer, and its input would be x third. So now let's again go back to the diagram. So if you see, we require output from some layers. So here, if we go to the first encoder block, so you can see the output from first residual block is also used as skip connection, and output from the second residual block is also used as skip connection. So we need to return those values, and if you see, pooling is also used. So let's go back to the coding part. So here we are going to return x1, x third, and p. Okay, so encoder block is done. So now let's try to implement our complete architecture. So first of all, we are going to implement this encoder part because it's really simple. Decoder is a little complex, not that much complex, just slight, because there's lot of skip connection. You can see, first of all, here we have simple skip connection. We just directly join at the concatenation layer. And another skip connection are like multi-scale features. So here we pass those features through transpose convolution and then we join them. So it's a kind of multi-scale fusion. So within each decoder block, we have simple concatenation and multi-scale fusion of features. So these shortcut paths provide a better flow of gradient during back propagation. So this would help in performance improvement. So let's define ColonSegNet. So we're going to say build ColonSegNet with an input shape as the argument. So first of all, we need to define the input layer. So we're going to say inputs equals to input, that is the layer, input layer. It's going to take input shape as the parameter. So our input layer is done. Now we're going to build the encoder. So encoder return three outputs. So we're going to say S11, S refers to skip connection, S12 and P1. And here we're going to say encoder block. First would be inputs, that is the input feature map, then number of filters. Number of filter would be 64. Then it's time for second encoder block. So this time we're going to say S21, S22 and P2 encoder block. So its input would be P1 and number of filter would be 256. Now it's time for the decoder block. So we're going to say first decoder 1. And let's go back to the diagram again. So if you see the diagram, the output of the second residual block from the encoder 2 passes through a transpose convolution where it's upsample feature by a factor of 2. If you can see, x4 we can also see the shape from 64 by 64 it is transforming to 256 by 256, and after that it is concatenated with the this S12, that is output of second residual block, and then a residual block. So let's implement these three layers first. So first of all, there would be a transpose convolution. So number of filters 128, kernel size 4, strides equals to 4. So here strides, when we say stride 4, so this means we want to upsample the feature map by a factor of 4, and padding would be same. Now we're gonna have our input to the con 2D layer, that is S22. So the transpose convolution layer is done. It is then followed by a concatenation. So now we need to concatenate it with S12. If you remember the output of second residual block from the first encoder. So we're going to say X equals to concatenate X with the S12. And then it is followed by a residual block. X would be the input and number of filter would be 128. Okay, so this part is done. Now let's again go back to the diagram. So now if you see, the output of this residual block would go into this concatenation block. So it would take the output of the residual block and this rest and the encoder 2 feature pass through this transpose convolution and this. So there are two things we need to know. So first of all, we'll take the output of the second encoder residual block passes through a transpose convolution. So let's implement the transpose convolution layer first. So let's say R1. We're going to save this feature X into R1, and then we're going to say X equals to con 2D transpose. So this time we're going to use this layer. So here we're going to upsample it by factor of 2, that is implemented in the paper. Our input would be S21, if you remember. Now we're going to concatenate. So we're going to concatenate this X and the R1. Remember R1, the residual block output, and after that it is followed by a residual block. X would be input and number of feature would be 128. So this is first a decoder. Okay, so this is the first decoder till here. So in each decoder you have a simple concatenation and a multi-scale concatenation. Again it is followed by the same procedure, nearly same procedure, same layer. Okay, see, after that followed by transpose convolution where we have X2, that is it upsample feature map by a factor of 2. See, 256 by 256 get converted to 512 by 512. Then a concatenation with the encoder 1 first residual block output, then a residual block. So let's implement these three layers first. So same as this above block, we can directly copy it. Let's copy it one by one. So first of all, we're going to say decoder 2. So it's easy for you to know what are we working on. So let's copy this because we have factor of 2. So we're going to say strides to 2. Now we're going to reduce number of input filters to 64. Our input would be X. Then it is followed by concatenation with S11. If you see, again go back to the diagram, S11 this, and then a residual block. X and then S11. After that it is followed by a residual block. So X would be the input and 64 number of features. Now again same procedure. Now it would have multi-scale concatenation. So this time it would take S12, passes through a transpose convolution and then concatenate, followed by residual. So let's implement this part. So we're going to save this x value in R2. So we're going to say R2 equals to x. Then a transpose convolution would be there. So let's copy this layer. So the input for this layer would be S12. S12. Then it is followed by concatenation x, that is output of this transpose convolution layer, and R2. After that it is followed by a residual block, x as the input, and 32 number of features. Okay, one mistake we have done. Within this transpose convolution layer, our feature would be 64 because we have to change the feature map accordingly. So our decoder 2 is done. Now we need to add the output layer. Output, a spelling mistake is there. So we're going to say output equals to, now here we're going to apply pointwise convolution, that is a 1 by 1 convolution. So number of output channel would be 1 because as we are assuming it's a binary segmentation task. Kernel size would be 1 and padding is the same. Okay, and because it's a binary segmentation, so activation function would be sigmoid. And your input would be x. So you're done. Now we need to build the model. So we're going to say model. So this model would take your input layer and your output layer, model function, inputs, then output. You can also give it a name. You can say ColonSegNet. Okay, this is done. Now we are going to return this model. So let's execute this cell. So your model is done. Let's try to implement it now. So you're going to say input shape. If you remember the function, this build ColonSegNet, take an input shape. So we're going to give exactly same height and width as we have given in this diagram, that is 512 by 512. So we're going to say 512 by 512, and let's say it's a RGB image. So now we're going to say model equals to build ColonSegNet. It's going to take the input shape. So this is done. We have initialized our model. Now to get what our model have, what kind of information it has. So we're going to print its summary. So you can see the input layer is 512 by 512, and gradually you can see the feature map starts to reduce. And inside this part is the squeeze and excitation part. Then it is followed by activation and all sort of layers. You can see how gradually the height and width of feature map changes, and when we come to the decoder part, it starts to increase, and at the end of this model we get our segmentation mask exactly of same height and width as our input image. So you can see these are the total number of parameter. So I'm really sure they are less than at least DeepLab, PSPNet and UNET also. This way we have implemented the entire ColonSegNet, and this is built specially for polyp segmentation, but it's not compulsory you're gonna apply it to biomedical segmentation. You can apply it to a normal natural image segmentation task also. But try to understand one thing here. For now this model is built for binary segmentation. In binary segmentation we have one output class. Let's say your task is multi-class segmentation. So here you would change this value, this output convolution layer number of channel would be changed from 1 to number of classes. Let's say you have 5 classes, so you're gonna say 5 here, and if I execute it again, you're gonna see, and one more change. Instead of when you have multi-class segmentation, you gonna change them to number of classes. Then activation function would also change from sigmoid to softmax. Let's execute it again. Now if we go to the end of the network, you can see a feature map of exactly same height and width, but number of channels have changed. And when you use this model to train, and accordingly your data processing and your loss function would also change. So I'm going to show you all those things in a next video. So that's it for this video. If you enjoyed it, then please subscribe the channel, like the video and share it with your friend. Thank you. Have a nice day.